Okay, so we're going to go and get started. I'm recording this lecture, so I want to get this party over with. I'll pick up where I left off yesterday, which is with the leukocytes. And about your leukocytes, they are the phagocytic white blood cells.
Alright, sorry to interrupt your awesome video. On like the second one where it was talking about like T cells, and it said one of the options, like A was leukocytes, but then that wasn't listed. It was E.
I think that's kind of what the problem was addressing, was what Ian said.
And what was the answer?
They were types of T cells. As far as other properties, I would say that your leukocytes were able to ingest pathogens. And then lastly, your leukocytes. What? They can be. Leukocytes can be attracted, or typically they're attracted to pathogenic chemicals. So like the evil, nasty chemicals that are produced by pathogens, there would be an attraction in that direction. And this list I'm about to go over is not exhaustive, but it's at least a decent start at a list. This is a list of some of the leukocytes that I think we should know. There's the neutrophils, and then the macrophages, and then lastly, the NK cells. And what does the NK here stand for? I'm sorry, what? Natural killer cells. Okay, awesome. And when we think of the term natural killer cell, and that's what this is, natural killer cell, what would it be killing? Like, what would be natural in this case? What? I think you're going the right direction. Natural killer. Exactly. Your own cells that have been infected with the nasty stuff. So a natural killer cell is going to be something that kills your own cells. But your cells, again, in this case, have gone rogue. They've gone crazy, essentially. As far as some other properties, your macrophages are the cells that are the big eaters. The natural killer cells are the types of cells that can kill, they are able to kill any virally infected cells. They can also kill cells that are cancerous. And very commonly, the way natural killer cells are able to act, the way they are able to make this happen, is by causing an apoptosis of the cell. So they cause the cell to undergo an event called apoptosis.
What do macrophages, where do they like evolve from again? Don't they like come? What?
I mean, basically big cells that go around eating things.
So we don't really need to know that.
What is apoptosis? So cell death, basically. And I think I want us to know the mechanism of this cell death. So again, these natural killer cells are able to recognize that your cell has gone bad, probably because it's become a cancer cell, or because it's become virally infected. And what they do, the mechanism by which they can do this is they release a chemical called perforin. So because of the release of perforin, which perforates or destroys the membrane. So again, this chemical's major purpose is to come in and result in the destruction of the membrane. Basically. Now, other mechanisms of recognizing that this cell's gone bad would be a little hard or a little difficult to do because you wouldn't know the cell's gone bad. It looks like a normal body cell. Remember, it was one of your cells that's gone and become something negative, but its outside still looks the same. So other systems, like some of the other lines of defense that we'll talk about, really would not adequately address this specific or this unique need. Good? As a reminder, what level are we on? Are we on second or third line of defense still? We're still on the second line of defense. So maybe at the top we might want to write that down, that we're still on the second line of defense. Remember, that was the type of defense system that was traveling throughout the blood, but it wasn't specific. It was not like an acquired type of immunity. Cool. Aside from having leukocytes, what was another, I don't want to give it away, but this probably what was another system that could be used as a second line defense? A system made of about 20 or so proteins. The complement system. The complement system is going to be another strategy, another system, much like your leukocytes, someone that can be patrolling the area, watching out for something negative. The complement system, again, is made of about 20 or so proteins. Found in the blood plasma. And what these 20 or so proteins do is they work to target bacteria and fungal cell walls. So these 20 proteins that we see here will work to target bacterial and fungal cell walls. And when you target those walls, what are you going to do to them, obviously? What would be the goal of these complement proteins? So destroy the wall, which results in the bacteria, the fungus, in dying. And aside from just having your leukocytes, the cells that go around and eat stuff, or your complement system, which are your proteins that recognize basically things that are not of this kingdom, not of the animal kingdom, you also have an inflammatory response, which we've really seen a couple times, I think, in the quizzes from yesterday and today both. So inflammatory response. When you have an inflammatory response, what are we talking about? What's going on here? Okay, so I like all that's through there, but first, before I talk about that, should we know this is a very specific or non-specific response? Okay, so it's a non-specific. And it occurs within a local area. So this is in a global bodily release of histamine, typically. This is a release of histamine in an area that is having an infection, having a pathogen in the nearby area. And it's non-specific in that, regardless of what pathogen's nearby, histamine would have been released. You're not specific in what chemical. And I think I had heard this from someone, actually from a couple of you. But when you release histamine, what happens to the blood vessels? Okay, so this is going to result in blood vessel dilation. So looking at like a before versus an after picture, post the addition of histamine, the before pipeline, pretty small, the after pipeline, much larger. So this blood vessel dilation obviously is a resulting in not just saying blood vessel dilation, you basically have a larger pipeline. And a larger pipeline, as you have gathered, can equate to basically more materials, whatever those materials may be. And for our focus, when we say more materials are coming to the area, I think our focus, what we be stressing in this chapter would mean that you have basically more immune cells in the area. Some other things that are happening when you have that inflammatory response is going to be an increase of temperature. And typically when we see an increase of temperature, that would be a condition where there would be a decrease in bacterial growth. We would also see a stimulation of phagocytosis. Good? Good, good? Good. Does anyone want these? Okay. Sure. Let's talk about your third line of defense. First off, as a review, what was your first line of defense? So the barriers, right? Wasn't just skin though. Skin and stuff. Could be the mucous membranes, right? Could be a tear. Even a tear was a first barrier. We learned that yesterday. Crying was a good thing because it contains what enzyme, which does what? Breaks down the peptidoglycan wall of a bacteria. So when you're crying, it's really not as sad as you think it is. Then the second line was going to be the non-specific patrollers of the cardiovascular system. He's about to cry over there. You realize that?
Okay, what is crying? I still don't even know.
What do you mean? People when they're sad they cry?
What is sad? What is crying? I don't understand.
We can talk about our emotions after class, I think. Okay. Your third line of defense, though, is going to be your acquired immunity. Or I might use the term active immunity. This is going to be a specific defense system. With some memory involved. It's going to contain two major pieces that we'll focus on. It's going to contain the lymphocytes, which would be your B cells and T cells. It's also going to be made of your antibody system. People this morning were coming up to me and saying, like, Mr. Fields, why don't you just use one or the other? Well, what if this system fails and you do end up with an infection inside the cell? You need to have a system that can kill a cell that's got that infection. Or you need to be able to kill the infection before it's attacked the cell. Good? Okay. Let's talk about some types of B cells. That's really pretty, isn't it? Or not? We're going to talk about plasma cells. And you can skip about 5 lines and then we'll talk about memory cells. What do your plasma cells end up producing? Perfect. They produce antibodies. Now, from these antibodies, you can produce your immunoglobulins. So your immunoglobulins are produced. Are antibodies specific or non-specific to a target? Very specific. So they are, or they must be, specific to a target. And because they're specific, that's kind of like going back that direction we've been down before, where it's all these different types of proteins that exist out there. So does that mean that for each issue, whatever it may be, each pathogen, would there be one global antibody or a bunch of unique antibodies? A bunch of unique ones, right? Since there's the specific key term dropped here, that means there has to be a bunch of different antibodies. So you have an antibody for chickenpox, and you have an antibody for flu 2008 style, then maybe flu 2009 style. Do you understand this logic? You have different antibodies for different stuffs. Just like I have different stuffs, but yet I have different keys for those stuffs. There's not one master key that I carry around that unlocks my everything. Right?
That would be sweet.
What? No, then I wouldn't have an analogy.
I'm sure you could come up with something else.
I'm a really simple guy. There's not much going on up here. So there's multiple types of antibodies. And I want us to make sure that we get that each target, or each will target, one specific antigen. Like a pitchfork? I don't know what that means. Cool? No. Oh, I see it now. Like Magic Eye. As far as your memory cells, what they provide is they provide you long-term immunity. Good. So these memory B cells are able to remind you how this system functioned, how you were able to destroy the invader. What was your strategy? Make sense?
I have a question though.
Sure.
So usually with eggs, they usually die from something like a common like cold or something.
That's correct.
Um,
How does that fit into this?
well, I know that AIDS attacks T cells.
Helper T cells.
Yeah. Well, so wouldn't your memory B cells be unaffected? Or?
That's true, but see, you'll see tomorrow that just because you have memory cells and you have like plasma cells, that doesn't mean that that system can be turned on. You'll see that helper T cells actually starts off, or is a connection piece between, and your book has a great picture, a little chart over. The T cells, helper T cells, are actually like an instigator of both of these systems. So like in the middle, helper T cells would exist as a positive direction for both of these guys. So if helper T cells aren't around, it's hard for your systems, your two independent systems here, to recognize that you have infection. Hence, it's like you still have your immune systems there, but it's blind. It's blind. Just to show you how this works in our last couple minutes, you have an invading cell, an invader, and your invader is recognized by both B cells and antibodies. So B cell and antibody recognition occurs. They are both derived from about the same piece, so yeah. Now what happens at that point is maybe there's one B cell that recognizes that you have this new invader. What will happen is this one B cell, as you've seen before, a B cell is something that can produce antibodies that can create these chemicals that can destroy an invader, but only one B cell, probably only a couple antibodies. So what we need to have is like an amplification system, a positive feedback mechanism that would result in the production of excessive antibodies. So we're going to do a successive series of cloning events. So the cells clone themselves, and this actually results in, if you think about it, tons of B cells as well as antibodies. Because as you have more B cells, you have more antibodies, right, Brad? Good stuff? Okay. And then they'll each serve their own purpose, or they'll serve a collective purpose. One is to attack and kill, of course, the invading cells or invading pathogens. Then the other one is to serve as a memory cell. Basically to exist as a reserve, awaiting to be called again in the event the pathogen shows back up. Now you've heard of people before having like catching a disease like a chickenpox and then getting it again, correct?
Yeah.
Well, the reason an individual might get it again would be if the B cells and antibodies that stick around post-infection, they could work out in such a way that maybe maybe your B's and your antibodies for that infection for chickenpox all go away. Random, unlikely, but if it does, then you could catch it again. But like I had the flu in 2008. I probably, if that strain of 2008 flu showed back up, it would be unlikely that I get it because I've got my cells that can remember how to fight it off. That's what immunological memory would be. Do what?
It probably won't come back when we say new strain.
It will probably be a new strain. That's correct. Because for any virus to exist in a population, it has to be carried in that population. And since most people have either been vaccinated or received the 2008 flu,
They already got over it.
that means they basically have the system that remembers how to fight it. It's like battle strategy.
So I thought by using that fire.
Actually dangerous.
I have a question about this person.
Hold on, let me hit the